Institute of Technology in Terre Haute, Indiana. He graduated with a Bachelor of Arts degree from Reed College in 1984. He received his PhD in mathematics, I believe, from the University of Washington in 1990. And he joined the faculty of Rose-Hulman in 1993. So he's done sabbaticals or research in other institutions, including NASA Langley. Was a sabbatical at Rutgers University and was a distinguished visiting professor at the United States Air Force Academy. He works on inverse problems, and he's very interested in undergraduate education. And it's part of the talk today on the $25 billion eigenvector is partly his interest in undergraduate education. I'm always interested in what people do to keep active as a triathlete, and the picture you saw on our advertisement was him competing in a triathlon, and it was not a selfie. His colleague did take the picture and send it to him, so I can allow you to speak since it wasn't a selfie.
Okay.
I always tell people I don't want to hear if you took a selfie because something will have to happen.
Okay. Okay.
All right, thank you.
Okay.
Let's join me in welcoming.
Thanks for the invitation to speak. I guess since my trip here is sponsored by the MAA, I'm supposed to make a little pitch for the Mathematical Association of America. So for faculty and students, for faculty, especially new faculty, it's a great organization to join because there's 2 conferences in Indiana, a fall and a spring conference. It's a great way to connect with other faculty members if you're new to the profession. If you're a student, I think it's like $10 a year for a student membership, and I think there's even institutional memberships where, like, if an institution joins, you get some number of students for free. For students, it's a great, these conferences in the fall and spring are also a great thing to go to because you get to start interacting with professional mathematicians. There's a mathematics competition at one time a year called the Friendly Mathematics Competition, intercollegiate competition. Students can give talks, you can hear talks. It's a great way to start getting involved in the profession. So the MAA is a good thing to join if you're interested in any way. So let me tell you about Google. So this talk stems from in 1997, roughly, when the internet was still kind of young. I remember Yahoo was sort of the search engine of choice at that time. And I remember going to Yahoo and I was curious. I typed in Rose-Hulman Institute of Technology into Yahoo and hit enter, and it came back with, even then, came back with a lot of search listings, even though that was 18 years ago. But when I looked at the first listing that it came back, the first hit it came back with, it turned out to be results, a web page that had results from a swim meet between like Rose-Hulman and Wabash College or something, and some guy from Rose-Hulman had finished 6th in the 100 freestyle in a swim meet. That was Yahoo's opinion of what it should present to me first when I searched for Rose-Hulman. And of course that made no sense because like Rose-Hulman's homepage was, as I recall, not even on the first page of listings. Well, the problem was, of course, that Yahoo at that time did not have a very sophisticated approach to deciding if somebody's looking for Rose-Hulman, what are they likely to want to see? Which web pages are the most important ones that I should present to them first? And that's one thing that distinguished Google when it came along in the late 90s, is it always seemed to give you the good stuff up front. The first hit was likely to be the thing that was most important. If you search for Rose-Hulman on Google, you get Rose-Hulman's homepage as the first hit back. So that's what this talk is about, is how does Google and how does their original PageRank algorithm decide what the most important web pages are? So, you know, a search engine like Google, it has to do 3 basic things. It has software that crawls around the web, and it collects information about web pages, indexes keywords on them, phrases, the structure of the web page. It indexes what pages that web page links to, what outgoing links it has, what other pages they go to. It collects this information, and I can see who hits my web page. I have a little monitor on it. I see their little Google bot, as it's called, come by every few days and index my web page. So all this data is collected. They have to store it in some suitable format, probably some massive drive farm somewhere. And then the part that this talk is about is when a user queries Google they have to go retrieve, says, I want to see rows, I want to find web pages with Rose Holman in them. Google has to go find those web pages in its database and then present them to the user in some kind of sensible order. And an essential ingredient in how Google chooses to do this is the importance of each web page. Okay, how important is each web page on the web? And this talks about how do you compute the importance of a web page? Well, here's what I want to do. I'm going to use this little sample web of 4 pages throughout the talk as a simple illustrative example. And if you look at this web, there's 4 pages, and these arrows have an obvious interpretation. They are links from one page to another. So for example, page 1 here has 3 outgoing links, one to page 2, one to page 4, one to page 3. This guy, so the link from page 1 to page 2, this is called a backlink for page 2. It's a link to page 2 from somewhere else. So page 2 has this backlink. Page 1 has these 2 backlinks, one from page 3, one from page 4, and so on. Okay? Those are called the backlinks. The goal here, rate the importance of each of these 4 web pages. The importance score for page 1, I'll call it x1. For page 2, I'll call that x sub 2, x3, and x4. I want these x's to be real numbers, and I want to scale it so if x sub 1 is 0, that would mean page 1 is a page of minimal or no importance whatsoever. And the bigger, more positive xk is, the more important page k is. Okay, so if you had to come up with a scheme for ranking how important these pages are, well, it makes sense that the more people that link to you, the more important you are. So one way to compute the importance of a web page is count how many backlinks it has. It's a very simple idea. So page 1 gets an importance score of 2 because there are 2 backlinks, 2 people link to page 1. Page 2, how important is page 2? 1. It's got 1 backlink. Okay, page 2 gets one back. It's the least important page in this web of 4. Page 3, you see there are 3 backlinks to it, so it gets a score of 3. That's the most important page in this web. And page 4 gets a score of 2 because it's got 2 backlinks. This is a very simple way you could try to rank how important a web page is, how many people link to it. But it leaves something to be desired because, you see, backlink counting yields those importance scores, and notice that page 1 and page 4 get the same score. Now, page 1 and page 4 both exchange a link with each other, so that's kind of a wash. But if you look, I could argue that page 1 should get a higher score than page 4, because the second backlink that page 1 has is from the very important page 3, whereas the second backlink that page 4 has is from the minimally important page 2. Okay, so page 1 and page 4 have the same number of backlinks, but page 1's second backlink is from the most important page on the web, page 2's is from the least important. And so this is like, if you have a link to your home page from Yahoo, probably that should boost the importance of your page more than a link from kurtbryan.com, which, by the way, I do not own. It's actually, and in fact, it doesn't even exist anymore, but it used to exist. There's a guy named Kurt Bryan who, he's a football coach, high school football coach in California, and he writes sports mystery novels. I just typed that in randomly one day. This is when my son was 2 years old. He said, put in kurtbryan.com, and he thought that meant there'd be a web page that told all about me. I said, there is no kurtbryan.com. There's a kurtbryan.com. It's this football coach. Anyway, here's the idea. We're going to improve this scheme. We want to incorporate the idea that links from more important pages should boost you more than a link from an unimportant page. So here's what we're going to do. Now this looks kind of abstract, but I'll show you in the context of that web of 4 pages how it works. But the idea is, here's page J and here's page K on some vast web of pages. Page J links to page K. So page J has effectively cast a vote for the importance of page K by linking to it. How strong is that vote? Well, that vote carries a strength of xj, however important page J is, but page J can't cast its entire vote for page K. It has to divvy it up into several pieces, in this case 4 pieces, because page J has 4 outgoing links. So page J takes its importance, x sub j, and divides it up into 4 pieces, or more generally, n sub j pieces, where n sub j is however many outgoing links there are here, in this case 4. It takes that x sub j over 4 in this case and gives it to page k as a vote for page k's importance. Okay? And the importance of any given page in the web, like page k, is going to be the sum of all the importance votes it gets from all the other pages on the web. So there's going to be an equation like this that says page k's importance is, and there's going to be a bunch of terms over here, each one corresponding to backlinks for page k. So let me show you in the context of this web of 4 here. Okay? How important is page 1? Well, the importance of page 1 is going to come from its 2 backlinks. One of them comes from page 3, one of them comes from page 4. Now, page 3, notice page 3 has a single outgoing link. Page 3 has taken its entire vote of strength x3, whatever that number turns out to be, and casts it for page 1. So page 1's importance is going to be x3 plus it gets a vote from page 4 as well. Page 4 has taken its importance score, x4, whatever that may turn out to be, divvied it up into 2 parts, and cast half of that for page 1. So page 1's importance score is going to be given by this equation, dictated by this equation. Again, it's got 2 terms, one because page 3 linked to it, and page 3 has only 1 outgoing link, so page 3 has cast its entire vote for page 1's importance. And then page 4 has cast half of its vote for page 1 because it links to it, and the other half it's going to cast to whatever other page it may have linked to on the web. Okay, so this equation is going to dictate how important page 1 is. Page 2's importance, well, if you look at page 2, do you see the single backlink for page 2 there? Okay. It comes from page 1. So page 2's importance is going to come from page 1. Page 1 has 3 outgoing links. So page 1 has taken 1/3 of its importance score and cast it for page 2. That's exactly what this equation says. Page 2's importance comes solely from the link it gets from page 1, but because page 1 had 3 outgoing links, only 1/3 of it gets donated to page 2. The other 2/3 are going to go to whatever other pages page 1 links to. Page 3's importance score looks like this. And of course, in each case, the denominator indicates how many outgoing links the relevant page had, and x1, x2, and x4, those indicate that page 3 is linked to by pages 1, 2, and 4. So that equation dictates page 3's importance. And this one, finally, if you chase this strategy through, this equation governs page 4's importance score. Now, if you look at this, we have 4 equations and 4 unknowns, x1, x2, x3, and x4. And of course, that's precisely because we have 4 web pages. 4 linear equations and 4 unknowns. The natural question to ask is there a solution to this system of equations? Okay, because that's what we're looking for. I want numbers for x1, x2, x3, and x4 to quantitatively rank how important they are. Actually, there's one obvious solution to this system of 4 equations and 4 unknowns. You see it? Easiest solution in the world. All zeros. Okay? Useless, of course. Everybody's unimportant. Okay, I guess it's a legitimate conclusion, but it doesn't help me distinguish which one I should present to the user first. Okay, the interesting question is, are there any non-trivial solutions, non-zero solutions to this system? And of course, there's other properties I'd like it to have. Like, I'd like the solution to be non-negative. And of course, in the end, I'd like larger values for x sub k to indicate that a page is more important in some defensible way. Okay, well, is there a non-trivial solution? Yeah, there is one in this case. Those 4 equations and 4 unknowns, this is one possible solution rounded to 3 sig figs, x1, 0.387, and you see the other values here. Curiously, in that web over there, you might think page 3 should be the most important because everybody else on the web links to it. Whereas page 1, in fact, turns out to be the most important. And the reason is, in this scheme, like it or not, page 3 cast its entire vote for page 1. So that equation I had a minute ago, let me show you this one. Page 1's importance is at least as great as page 3's importance because page 3 cast all of its weight to page 1, and then page 4 threw in something, and that pushes page 1 over the top. It makes it bigger than page 3. So page 3 turns out to be the second most important web page in this case. And of course, page 2 is, as you might expect, the least important page. And page 4, well, and notice page 4 is now about half as important as page 1 in this scheme. Previously it was a tie, now it's only half as important as page 1, because page 1 has that powerful link from page 3. Well, okay, so here's the question. How did I come up with this solution? And will there always be such a solution to this? If I draw a larger web with a more complicated link structure, will this crazy scheme of ranking web pages like this, will there always be some solution here? Because if you write down 4 equations and 4 unknowns randomly of the form that I had there a while ago, probably the only solution is going to be all zeros. Turns out in this case, though, the structure of these webs guarantees there will be a non-zero solution. By the way, I do want to point out one thing here. These numbers are all, I scaled these numbers so that they add up to 1. If you add up all these important scores, they add up to 1, rounded off to at least 3 sig figs. And if you think about it, the equations I wrote down, if I multiply the solution by 10, if I multiply each of these numbers by 10, it's still a solution to those 4 equations and 4 unknowns. Here, check it out. Look at these 4 equations and 4 unknowns. Multiply every single x in sight by 10, or 100, or 37.8. The equations remain true. If you have a solution and you multiply every component by any scalar, any number, the equations are still true. So when I came up with this solution here, only their relative values really matter. So if I said x1 is 38.7, x2 is 12.9, 29.0 and 19.4, that's just as legitimate a solution as this one. Okay, it's the relative values that are actually going to be important. Okay, so how did I come up with these numbers? Well, okay, our sample web had 4 pages, and so that led us to 4 equations and 4 unknowns. You can solve 4 equations and 4 unknowns using, just high school algebra, Gaussian elimination, or you could do it on paper using, eliminate one variable at a time. It hardly matters. 4 equations and 4 unknowns is no big deal. But see, Google's task is to do this for maybe tens of billions of web pages. Well, if you try to do Gaussian elimination, of course this results in a matrix that has or in a system of equations, I should say at the moment. This results in a system of equations that has tens of billions of equations and tens of billions of unknowns. If you try to use standard Gaussian elimination or anything, you can't do it. It's too slow, and you can't even store the equations. There's too much memory required. Okay. It turns out you can solve these equations with an iterative approach, and I'll show you what I mean by an iterative approach. So forget web page ranking for the moment and just think about high school algebra. If you want to solve an equation like x equals f of x, so for example, maybe you want to solve, and I use this as an example, maybe you want to find a solution to this equation. Find a number that's its own cosine. Okay? In this case, x is said to be a fixed point for the cosine function. More generally, if you find a solution to x equals f of x, okay, x would be a fixed point for f. It's in goes x and out comes x. Okay? Well, fixed point iteration is frequently a good way to solve these kinds of equations. Okay? Here's what I mean. Okay? You want to solve x equals f of x. Take a guess at the solution. Guess x equals 1. Anything. Okay? Now, take that guess and plug it into f. Okay? Take that guess and plug it into f. And compute the output. So plug in 1 into f, and compute the output, f of 1. Take that and feed it back into f. That's what this iterative scheme here is saying is, over and over again, take the output and feed it back into f, and compute a new output, and feed it back in. And I'll show you an example of this with the cosine function. And at some point, if you're lucky, the z's will approach a fixed point for this equation. That is, they'll stop changing and settle down to a solution to x equals f of x. So for example, okay, if you start with the cosine function, and plug in 1 as your initial guess at the solution. Okay, plug 1 into the cosine and compute the cosine of 1. You get 0.5403. Take 0.5403 and plug it back into the cosine. Now you get 0.8576. Take that, plug it back into the cosine, and keep going like that. Just keep taking the output of the cosine and plugging it back in as the input. And by the time you get to the 20th and 21st iterations, you see out here it's stabilizing to more and more decimal places. This is called fixed point iteration for solving an equation of the form x equals f of x. It's not guaranteed to work, but it frequently does. Okay, now, and my introduction to fixed point, this is also a way to generate random numbers. This is a general methodology for computing random numbers, which I read about in high school and tried to program, and then I got a rude awakening to the idea of fixed point iterations because my random number generator always settled down to reproducing the same number over and over and over again. So, anyway. The iterates converge to a solution of x equals cosine x, okay? We're going to take this approach to solving those 4 equations and 4 unknowns for Google, okay? These 4 equations and 4 unknowns, it's a kind of a fixed point iteration, because here's what we're looking for. I'm looking for 4 numbers, x1, x2, x3, and x4, such that when I jam them into the right-hand side over here, out come the original 4 numbers that I started with, okay? That's what I'm looking for. So I start off by just guessing at a solution to this system of 4 equations and 4 unknowns. So I'll start off with 0.1, 0.3, 0.5, and 0.1. I'll take those 4 numbers and I'll just plug them into the right-hand side and see what comes out. Okay? Well, what comes out is these 4 numbers. Okay? I call these the update to my initial guess. I'll take those 4 numbers and then I'll plug them back into the right-hand side and see what comes out. What comes out are these 4 numbers, 325, 183, 292, and 0.2. Those are already precariously close to the numbers I listed earlier for the web page importance scores. If you do this over and over and over again, here's what it looks like. Okay, here's 4 columns indicating the four numbers. My initial guess, iteration 0, was 0.1, 0.3, 0.5, 0.1. Each time you iterate, look at what happens. I take those 4 numbers, I jam them into the right-hand side, and I see what comes out. By the time I get to the 10th iteration, I've already settled down to 3 significant figures on each of those. I've solved the system of 4 equations and 4 unknowns in the ultimately easy, brain-dead way. I just keep I take my latest iterate, I jam it back into the right-hand side, I compute the left-hand side, and I keep going until everything is stabilized to my satisfaction. Okay, If this is all you get from this talk, you've seen the core of Google's PageRank algorithm as they originally presented it. Okay? That's methodology of taking a web of pages and computing each page's importance score by considering the links from the other pages as votes, weighted votes from those pages. That leads to that system of 4 equations and 4 unknowns, or 10 billion equations and 10 billion unknowns. And then you solve that system by using this iterative scheme. Take a guess, plug it into the right-hand side, compute the left-hand side, and just keep feeding it back into itself until it stabilizes. That is the guts of the PageRank algorithm. But there are some nuances, like why does this converge? And will it always converge? Or can I write down a web where it doesn't work? And the answer is, yeah, I can write down a web where it doesn't work. There's a modification to this that they made that safeguards it against, going crazy. But that's what I want to show you now. Why does it converge, and what can we do to make it converge faster? And also, what can we do to make this efficient on a 10 billion by 10 billion system of equations? Okay, now, these questions are best addressed in the context of matrix or linear algebra. So, if you've taken a linear algebra course before, great. Then you know what matrices are, and this will be transparent. If you haven't taken linear algebra before, well, I'll give you a short, bare-bones introduction to what you need to know to understand what is a matrix, what does it mean what is a matrix, and what does it mean to take a matrix times a vector. That's the key of what you need to know. And you can consider that as inspiration for why you should study some linear algebra and make your life much easier. Okay. So, the language of linear algebra. So here's your crash introduction to linear algebra. Okay, first of all, those importance scores that I wrote down, x1, x2, x3, and x4, I'm going to amalgamate them into a single object, a vector, and I'm going to write my vectors in this form, column vector. So my web of 4 pages gives rise to a vector that's 4-dimensional. If I have 10 billion web pages to rank, then I end up with a 10 billion dimensional vector. And of course, I call this amalgamated